Hi and welcome to the second video in the series, The Geometric Approach to the GCD. In this video, we will extend the method of solving linear Diophantine equations with two variables using a linear algebra approach to equations with n variables. If you don't know this method, I recommend you to watch the first video of this series, and the link is in the description. Here is a summary of the method. We start using the Euclidean algorithm to determine the GCD of A and B. Then we transcribe each quotient ki from the Euclidean algorithm steps into a linear transformation x to the power of ki minus 1 times r, where x and r are the elementary linear transformation deduced from the linearity of the GCD. For the last step, we use x to the power of kn minus 2 times r to ensure the GCD remains as the final remainder. The total transformation will map a square of side D to the rectangle A times B, and is the product of the transformation from each step. The inverse transformation maps the rectangle A times B back to the unit square. The rows of the inverse transformation matrix correspond to the solution of the Bézut's identity AU plus BB is equal to GCD of A and B. Since the Bézut identity has infinitely many solutions, the inverse matrix provides a general solution, where n and k are any integers, and the determinant of the solution matrix is k. Note that the original transformation is not unique, as demonstrated in this example. In the first video, we built two elementary matrices that preserve the GCD of two integers using the linearity of the GCD. The first transformation can be visualized as an extension of a rectangle with sides A and B, and the second by rotation of the rectangle. For the GCD of three numbers ABC, we start with a cube of dimensions A, B, and C. Unlike two-variable case where only two linear relations define the GCD, there are many more relationships for three integers. Intuitively, this is because extension and rotation transformation can be applied to each face of the cube AB, AC, and BC, while keeping the third dimension constant. We define a transformation matrix for each relation. Some matrices are composition of others, as we can see here. All these matrices with determinant of plus minus 1 are unimodular matrices which preserve the GCD when applied to the vector A, B, C. Two matrices with zero determinant demonstrates what happens when the GCD is no longer preserved. You can test these with vector 1, 2, 3 to see the result. But since the Euclidean algorithm cannot be used to find the GCD of three integers at once, it is difficult to define a method using these matrices to build an overall transformation which maps the vector 1, 1, 1 to a given vector ABC. But we still can find such transformation without calling on these matrices. Let's consider three integers A, B, and C, where the GCD of A and B is equal to 1. By Bézut's identity, if the GCD of A, B, and C is equal to 1, there exist integers x, y, and z such that ax plus by plus cz is equal to 1. To build a transformation matrix that maps 1, 1, 1 to ABC, we need a 3 by 3 matrix with two requirements. The sum of the rows are the values of A, B, and C, and the determinant of the matrix is equal to plus minus 1. This matrix will map the vector 1, 1, 1 to the vector ABC, and the inverted matrix will map the vector ABC back to the vector 1, 1, 1. And the rows of this inverted matrix will be the solutions x, y, and z to this Diophantine equation. To build this matrix, we start by building the unimodular matrix T of A and B that maps 1, 1 to AB using the Euclidean algorithm. And the determinant will be plus minus 1 by definition. Then we construct a block matrix with T of A and B in the top left block, zeros in the top right block, 1 in the bottom right corner, and the bottom left block ensuring the row sums equals C. So this matrix will map the vector 1, 1, 1 to the vector A, B, C. And since the determinant of this matrix is the determinant of this upper left block times the determinant of this bottom right corner, the determinant of this matrix will also be plus or minus 1. The inverted matrix will map the vector ABC back to the vector 1, 1, 1, meaning that the rows of this inverted matrix shown here are the values x, y, z, which are the solution to this Diophantine equation. Let's do a quick example. If the GCD of 17, 27, and 37 is equal to 1, there exist x, y, and z such that 17x plus 27y plus 37z is equal to 1. And we know that the GCD of 17 and 27 is equal to 1. So we start by computing the T of 17 and 27 using the Euclidean algorithm and transcribing the steps into transformation x to the power of n minus 1 times r as saw previously. Then we build the block matrix and calculate its inverse. The rows of the inverted matrix is the solution to the Diophantine equation 17x plus 27y plus 37z is equal to 1. We can tune W to find possible sets of x, y, and z. We choose here a W to have the smallest numbers on the last row, and this will give a possible matrix mapping 1, 1, 1 to 17, 27, and 37. And the inverse will map 17, 27, and 37 back to 1, 1, 1. As we see here, we can choose any number for W. And for each W, we have another set of x, y, and z. In a future video, we will see that we can have other values for z since we are going to find the general solution for such Diophantine equations. This block matrix approach can be extended to more than 3 integers. If the GCD of A1, A2 up to AN is equal to 1, then there exist xi's such that the sum over I from 1 to the n of ai times xi is equal to 1. If we assume that the GCD of A1 and A2 is 1, we can define a unimodular matrix T of A1, A2 using the Euclidean algorithm and the elementary matrices X and R. This matrix will map the vector 1, 1 to the vector a1, a2, and its determinant is plus minus 1 by construction. Then we build our block matrix, but this time at the bottom right corner we have n minus 2 times n minus 2 unimodular matrix. The determinant of this matrix T is the product of the determinant of matrix A times matrix B. And since we want T to be unimodular, A and B also must be unimodular. The rows of the inverse of this matrix will be solution xi's to this Diophantine equation. But since this is a special kind of block matrix, its inverse can be calculated quite easily, as shown here. And if we choose B wisely, we can simplify the computation cost a lot. One of my favorite choice for the matrix B is an identity matrix with minus 1s on its subdiagonal. The determinant of this matrix is 1, and when we invert it, it becomes a lower triangular matrix with all elements equal to 1. The other advantage of this matrix is that the sum of the rows are 0 except for the first one. But again, you can use any unimodular matrix for the block B. Now let's do again a quick example. We choose a set of numbers 17, 27, 37, 47, 57, 67, and 77 with the GCD equal to 1. And this is the associated linear Diophantine equation. The GCD of 17 and 27 being 1. We start again by calculating the transformation matrix of 17 and 27 using the Euclidean algorithm, and then we build our block matrix as explained. We have this T of 17 and 27 matrix here. We have by our 2 by 5 0 matrix here. We have our B matrix here, and here we have some free variables such that the sum of the rows are corresponding to 37, 47, 57 up to 77. If we can choose any numbers for these UIs, but we can again minimize them and have nice values for them. So we will obtain this as the matrix mapping the vector 1s to this set of number, and the inverse of this matrix with rows being the solutions to this Diophantine equation. If we don't substitute the UI values, we will obtain such an inverse matrix. And we can see that we have solution to the Diophantine equation of 3 of them, 4 of them, 5 of them, 6 of them, or all of them in the same matrix. Again, we can use any unimodular matrix for B in this block matrix. And the general form of the matrix is shown here, with Ri's being the sum of the elements of the ith row of B. In the inverse of this matrix, we can see that the elements of C blocks are related to the dot product of A3, A4 up to AN, with the rows of the B matrix -1. These elements can also be reduced by multiples of A1 and A2. But this structure gives another information which makes the solution to the Diophantine equation related to the GCD of A1, A2 up to AN quite easy, as we will see in the next slide. Let's consider our example set and its related Diophantine equation. Let's define f as 1 minus 37x3 minus 47x4 up to 77 times x7, where x3 up to x7 are any integer. The general solution to the Diophantine equation is on the following form. So we only have to find x1 and x2 solutions to the Diophantine equation 17x1 plus 27x2 equal 1, and choose any other number for x3, x4 up to x7. And this is true as long as there is at least 2 coprime elements within the set of integers ai, as we see here. But what will happen if there is no coprime pair in the set? This is what we will see in the next video of this series, where the absence of the coprime pair in the set can make this method fail. But there is a solution to this. Thank you for watching, and I look forward to your comments and feedbacks. Bye.